So I have a couple of functions here. I mean, I am writing them as if they are autocorrelations. So let me ask you something. Remember, we know the relation between autocorrelation and power spectrum. The Fourier transform of autocorrelation represents the power spectrum. So power spectrum is the Fourier transform. So this is Rxx omega, I mean tau e raised to minus j omega tau d tau. And we have, unlike other functions, the Fourier transform of an autocorrelation function is non-negative, and we have gone through all the properties. So if you suspect a function to be autocorrelation function, it's very difficult to look at it and decide. So what is an easy test? How will you test it, whether a function is autocorrelation or not? Right, how will you, that's going to be a little hard to test it because you have to go through all that matrix stuff and all that. Whereas here is an easy test. What do? Find the power spectrum. So you just have to do the Fourier transform. Then physically look at it and see whether it is positive or not. So a power spectrum should be above the line. If it goes negative, then you know that trouble is here. This cannot be a power spectrum. Consequently, that function is not an autocorrelation function. So let me ask you this. Is this an autocorrelation function? Valid autocorrelation function? If I draw this in, is this an autocorrelation function, Mike? It's a question to you. Why not? So let's take its transform. What is its transform? Sinc. Sinc, you see, if you draw sinc, sinc goes positive and negative. This cannot be a power spectrum, so this cannot be a auto. So let me ask you this. What if I put the sinc function here? Can this be an autocorrelation function? Why? It's very difficult to use your technique here. How will you know that this is a non-negative definite? But on the other hand, it's a spectrum, at least qualitatively, is like this, right? We went through this, right? So spectrum is positive, and consequently, this is a valid autocorrelation function. This is not a valid autocorrelation. How about this in time domain? A triangle. Valid autocorrelation or not? Anybody? Why?
Because it's 6 squared.
Only, very good. So that's good. So this, so you see, you need to know the properties. Then it's sinc squared omega. So whatever it is non-negative. So you know this is. So how about these functions? So it's very difficult to look at it and decide. Sometimes you can simple things like this. So what if I had sinc squared here? Anybody? Autocorrelation or no? Why?
It's like triangle.
This means what? What did you say?
Like a triangle.
What is triangle?
It's a Fourier transform.
Very good. So sinc squared Fourier transform, remember we went through this, is the convolution of a rectangle with rectangle. So that's a triangle, but it is positive. So it's how about sinc cubed? So everything is good, right? Okay, so let's look at, so I think all these problems are there on the, so e raised to minus alpha tau looks like what? This function looks like this, right? Right? No? So this is the way the function looks in time. How about here? How does this look? I mean this one. This one. Like this, right? How about here? So looking at this, both look similar, but they are different B's, right? One is sinc. Sinc is modulated by this. But the question is, are these autocorrelations? I don't know, we will have to do it and see, right? So we have to do the Fourier transform and so if you take the first one, so let me call this R1, R1, R2, let's say this is R3. Actually, the question is, we don't know whether they are, so let me look at the Fourier transform of the first one. So that's minus infinity to plus infinity, e raised to minus alpha tau tau d tau, right? Now, this is supposed to be your job. I shouldn't be solving it, but I'll show you one. And as I said, I think all of them are solved here and there on the videos. So this is an even function, right? So we want to exploit even property. Look at this. So if you expand this, this is cos plus sine. So what can I write this as? Anybody? Plus what? Yeah, minus j e raised to minus alpha t sine omega t integrated over minus t to plus t. What is that integral? Because this is an even function, this is even, sine is odd, even multiplied by odd integrated is 0. So this is this, okay. Now this whole thing is even, right? So I can integrate, I don't have to integrate this over. Is this true?
Yes.
So what do I write here? What did you say? Plus? Why didn't I put the absolute value here? Anybody? Because it's in the positive side. So I can get it, because absolute value is a non-linear operation, so I can get rid of the absolute value here. Okay. Now you can, many ways you can do this. You can do it by part, but let me show you a quick way of doing this. See, this is a real number now, right? Real number. So can't I write like this? Yes or no? Is this true? Real part of this number is what? Real part of this is cosine. Right? If I multiply by a constant, that doesn't change, isn't it?
Why omega becomes omega now?
No, it should be omega, right? I'm thinking of the second problem already. You see, so this is only just to do it. You can do it by parts, you don't have to. This is just a trick. So you 2 times the real part, integral 0 to infinity, e raised to minus, what is it? Alpha plus j omega t dt, right? So you see, because dealing with cosine is a little harder than e raised to j omega t, cosine is the real part of this. And this is a constant. If this was complex, I couldn't do this. It's a real number, so the real part of this whole thing is actually what you have there, e raised to minus alpha tau cos omega tau. See, this is very easy to integrate. So this is now 2 times the real part of e raised to minus alpha plus j omega t 0 to infinity alpha plus j. So look at here. When you put the top limit, because alpha is real, that is gone, right? What is the value of this integral? Anybody? Top limit is 0, right? Why? When you put it here, this is going to oscillate, but this goes down to 0 very fast, right? Minus alpha t. So what is the value of this? 2 times the real part of 1 over alpha plus j omega. So what's the real part of this? So that's alpha minus j omega over alpha squared plus omega squared. 2 times the real part. So the answer is 2 alpha over. This you must have seen earlier, maybe you were junior or somewhere, right? So look here, This is a positive function, right? So only at this point I conclude that's a valid autocorrelation function. And let me do one more. And then we'll pick up the rest. So you try to solve it, and then so the second one is equally easy. Let me the cosine omega naught tau, right? So you have a cosine omega naught tau. All this goes through. You have a cosine omega naught tau. Yes? Then what? Then you have a little bit job to do, because this is not the real part of something. This has to be written as cos A cos B is what? You forgot? Cos omega plus omega naught t plus or minus? Cos omega minus omega naught by 2 over 2, right? So you see, you get two integrals. You go home and do it. Each integral is, of course, of this form, right? So you can again use this real strand and put it together and see whether the thing turns out to be positive. Okay. Let me do the more interesting problem, and after that we'll stop. So I have a function right? So since it's being multiplication, the time domain, it is convolution. This we already know the Fourier transform, right? 2 alpha over alpha squared plus omega squared. Convolved with, what is the Fourier transform of sinc tau? Anybody? Fourier transform of sinc t, sinc alpha t. We just did it.
Yes, it's a square.
Square? This is a square, right?
Yes.
I think it is alpha over pi. Let me see. Pi over alpha.
Oh, yes.
All right, so that's going to be, so let me call this to be h of omega. So this is going to be convolution of this function, right? This is your S1 omega. So S1 omega convolved with this one. So this is S1 of omega minus x, right? H of x dx, right? In general, like this. This is just a dummy variable, right? I can put here tau, but I don't want to confuse you, right? So this is S3 of omega would be 2 alpha over alpha squared plus omega minus x the whole squared. All right, so hx is going to go from minus alpha to alpha, right? That's hx. So this is simply of pi over alpha. So alpha cancels. And let me put omega minus x to be y. Then you see so when x is minus alpha, this becomes omega plus x, right? So this is omega plus alpha, omega minus alpha, and this is 2 over pi alpha squared plus y squared dy, right? Minus dx, dx is minus dy. So if minus dy, so these limits will again flip and it will become like this, right? That much is correct. Now, of course, you know how to do this integral, right? So what is the substitution I would do? Anybody? Very good. So we put y equal to alpha tan theta. So dy is y. So there is some doing to be done here. It's an interesting problem. I found it somewhere. So this is 2 over pi is a constant. So the numerator dy is alpha sec squared theta d theta, right? Denominator is alpha plus 1 plus tan squared, right? So this cancels with this, alpha cancels, everything cancels, right? Then you can go home, right?
Yay.
All right, so let's substitute for the limits. So look here. So y is the lower limit is omega minus alpha. So what is the lower limit alpha? Yeah, so this will be tan inverse of omega minus alpha over omega minus alpha equal to alpha tan theta. So what's the lower value? Right? And here this will be tan inverse of, right, omega plus alpha over alpha. All right, so it looks like you can write this as tan inverse of omega plus alpha over alpha minus, it's a mess, right? We don't know, how do you know whether this is positive or negative? So we have to do a little more work. So that much is good. So I'm going to call this whole quantity to be A, okay? So let me call A to be tan inverse omega minus alpha over alpha. So we want to check this, right? This is what we want to check, whether it is positive or not. Remember how I got this? Because this is just a d theta. D theta is theta, so top limit minus bottom limit, right? There is. All right, so from here you see, I can write this as the first term, tan inverse of omega plus alpha over alpha is, A is what we are trying to find out, so, right, this much is true, right?
Yes.
So you get, let me push this tan to the other side, right? So I'm going to take this tan to the other side. So you have omega over alpha plus 1 tangent of two terms, right? Tangent of A plus C, right? Let me call this to be C or B. What is tan A, tan B? Anybody? This is tangent of, this is A plus B here. So when I bring in the tan inverse, this is tan of A plus B, right?
Yes.
Hello? So how do you expand this? You forgot? Tan. Oh, anybody? She forgot. Tan A? Tan A plus B is what?
One minus tangent cancel.
Oh, so somebody is, there is some hope. Somebody remember. Now I am going to cross multiply. See, remember I am trying to figure out what this A is. So let's cross multiply this. So I get this multiplied by this. So I have 1 minus tan A. Look here, hold on. This is tan inverse, right? Nobody is paying. So what is tan B? Anybody? Tan of tan inverse of this. So it is this, right?
Yes.
So tan B, of course, you see it as omega over alpha minus 1, right? Right? So 1 minus tan A multiplied by omega minus alpha. So this multiplied by omega over alpha plus 1 equal to tan A. Tan A is what? Tan A is tan A, right? Right? You can see a lot of cancelling will go on. So there will be 4 terms here, right? So 1 plus omega over alpha, then what? Plus 1, right? I'm going to multiply this with this.
Okay.
I'm going to multiply this with this. So this is minus tan A. Is it? So this cancels with this, right? And this one cancels? No. What? Oh, here. Look at this. This is x minus 1, this is x plus 1. So this is omega squared over alpha squared minus 1. Yeah, look here. This one multiplied by yeah, you may be right. Hold on, let's see. So 1 multiplied by this, that's this, right?
Yes.
Okay. Minus tan alpha, this thing multiplied by this, so it is this. You're right. Yeah, probably. Okay. And here this is fine, right? This cancels with this, right? Let me take the tan alpha to one side. So I have tan alpha equal, tan alpha multiplied by omega squared over alpha squared minus 1. I'm going to take it to this side, plus 1 from here, right?
Yes.
Tan alpha plus 1 equal to 1, isn't it? 2? Why? This one is still here.
We have a minus.
Okay, so this will be 2. Right. So I'm going to bring it over. So this one and this one cancels. So tan A is what? 2 alpha squared over omega squared. So A is tan inverse 2 alpha squared over omega squared. And tan curve goes like this, right? So if this is your omega, your tan inverse of omega is here, right? Here only, which is positive. So this quantity is positive. So what's the bottom line? That complicated, the power spectrum of that is, it's actually a valid autocorrelation function, but it takes some doing. So that's the hardest one, the third one. Second will be easy. I think I did this right. If you want a small twist, which is what I have here, so if you feel like you change the alpha to beta and see what, so this is the question now, look here. This alpha, you change it to beta, And question is, what are the, for what values of alpha and beta will this be a power spectrum? So you have to, exactly the same way, but at some point you have to make sure that some quantity is positive, and that will give you the, I think alpha need to be greater than beta or something, I don't remember, but it is there. So the question is, for what values of alpha and beta this represents a valid autocorrelation function. Okay.